Hi everyone. The video you're about to see is a clip taken from one of the classes that I ran last Friday, I think it was the 20th of March, where we were discussing the COVID infection numbers, the rate at which they were growing in the US, UK and Italy. And based on our mathematical analysis of these three countries' infection numbers, we came to the conclusion that US would soon overtake Italy. So seeing as on today, the 25th of March, the US numbers are rapidly catching up with that of Italy, I thought it would be interesting to share this video with everyone so that you can see the importance of having some basic maths knowledge. So without further ado, please enjoy.
So what I'm trying to do here, right, is I actually did some analysis for USA and Italy, and today I noticed that the UK numbers are out as well. And so I thought I would do a little bit of analysis and see whether we can tell if the numbers of COVID cases, right, are growing faster in Italy versus USA or versus UK. Okay, so the background is this. The current situation is no, don't do this. Sometimes very scary, this program. Okay, so the current case, this is not the latest numbers. This was the numbers that I got from yesterday. Right, yesterday they only gave up to 18 March. So the cases are like these. Current cases in USA versus Italy is like 9,000 plus versus 35,000. So on paper it looks like Italy is more jialat, more in bigger trouble. But you have to note also, right, that the exponential growth phase of the COVID-19 numbers in US kind of started a bit later than the Italy numbers, right? So it's like it's still at an earlier stage in US versus Italy. So how do we figure out which country is in a better position or worse position? Okay. First of all, right, we want to try to figure out what is the equation of that graph, the exponential growth curve, and we can do a little bit of deriving here. Okay. So first of all, let's try to imagine what happens. So let's say for every infected person, right, they go out into the community, go about their daily business, and then they meet some people, and then out of these people, maybe there's a chance of infecting someone else, right? So maybe, right, let's say let the number of people, right, that is infected by this one person every day, let this number be k. So let's say if we have a k value of 1, right, that means each infected case, right, on average will infect one new person every day. Okay. And so what this means is that if we start off with 100 people infected on day 0, then by the time day 1, right, these 100 cases, each of them will infect one new person, right, out of all the people that they interact with. Okay, and then we will have a doubling every day, right? You can see that then 200 people will infect another 200, and then brings the total 400 and so on, right? But if you look at the numbers, obviously that's not the case, right? So likely the true value of k will be 0 point something, some fraction. Okay, and 0 point something doesn't mean that everybody goes out and infect half a person. You can't infect half a person. Okay, what this means is that some of the infected people do not pass on the infection. Okay, so from 100 cases on day 0, maybe you will create 50 new cases, 50 new infections. And then from 150, you will create 75 new infections and so on, right? But again, each day you will see that the number of infected cases, right, actually grows. This one should be like 113, right? The number of the new infections will increase as well. Okay. So if we try to put this into a generalized equation, right, it will look something like this, right? N1, this is number of infected cases on day 1, equals to original number of infected cases plus k, which is this k number that we assume as 0.5, times the original number, right? Correct? Which we can then, factorize into something like this, right? And then N2, you follow the same pattern, but now the basis is based on N1's number, right? Day 1's numbers, and so on and so forth. Now, if you carry on this idea, right, you will start to see some kind of pattern, right? N1 equals to N0 times 1 plus k to the power of 1 right? And then this one times 1 plus k to the power of 2, like 1 plus k to the power of 3, and so on. Right, so we can write down in a generalized equation like this, right? N at after t days, right, on day t equals to the original number of infected cases on day 0 times 1 plus k bracket to the power of t number of days, right? So this is our exponential equation, right? The dependent variable is this one, number of infected cases on any given day is dependent on this independent variable, number of days that has elapsed, right? And it's controlled by these constants n naught, which is the original number of infected cases, and k, which is the a factor of how quickly the virus is spreading. Okay, and so our goal, right, is going to try to look at this k value, right? What is the k value? Is it the same across the board, or does it differ from country to country, right? If it differs from country to country, then basically a bigger k value means that it's spreading faster, right? So we can take data and now in order to find the k value, we can't just use this equation, right? If we plot this on the graph, then basically we will just get this graph like that, right? And then this graph, like from a curved graph, it's very hard to tell like what are the constants, right? So what do we have to do? We have to, everybody's holding their breath. Do you all know how to do this? What do you have to do? When we do practical, you all haven't started doing any practicals yet, right? Started already? Oh, you all started already? Your school? Not yet? Agatha? No, not yet. Okay. Yeah. So for you, this will be something new. For Diksha and Yanning, you all know what to do. What to do? Linearize the graph. Okay. Yes. So for practicals, right, when we try to find constants from some not fully understood mathematical equation, it is always useful to draw a straight line, plot a straight line. Okay. So if the original equation, right, is not possible for us to plot a straight line, we have to do some modification to the equation to enable us to plot a straight line. And this process is called linearizing the graph, lah. So in this case, because we are trying to plot something that has to do with nt versus something that has to do with t, right? And t is in the power. What we have to do is to take log on both sides, right? And so if we take log on both sides, then t comes down from the power, right? And then we can basically plot it like this. So we can plot log nt versus t, right? And this will give us because once you log it, right, this becomes the form that's generally like y equals to mx plus c. Right, so this log n naught will become your y-intercept, and this log bracket 1 plus k will become your gradient. So basically when we plot these two, this one and this one, we plot these two, we find the gradient of the graph, and then from there we can use that to find k. Right? So data, like I was showing you just now, I one by one copy from this series, right? But I have to find, I'm plotting log n versus t, right? So I have to do a conversion first, log n. Now, I was telling you all just now, right, those that came early, that normally this is the very annoying part in your practical where you have to do the same calculation many times for different set of values, right? So that's why programs like this are so great, because they allow you to do it once and then basically just repeat the same calculation for a whole set of values like that, right? So you have 33 set of values all done in just snap of fingers. Now, later on I will show you how to do this on your graphing calculator. So anybody, only Agatha, you have a graphing calculator? Now I have a virtual calculator here that I can show you how to do it as well. Okay. Okay, so now what are we going to do? Yeah, we were going to plot log n versus time t. Okay, so again, I'm not going to do this on graph paper because it's going to take like 1 whole hour or something. So let me get the program to do it for us. this one, plot against this one, insert graph, scatter plot. Okay, so you can see that this graph not exactly a straight line. We were expecting a straight line, right? Remember? So over here you can see kind of flat first, and then after that this region looks like a very nice straight line, right? So the thing is, I will have a tendency to want to ignore these first few points of data, and the reason why is because at the start of the outbreak, right, maybe there's not a lot of public awareness yet, right? And then, you know, hospitals are also not very ready with the test kits. Maybe people are sick and they're not going to the hospital to get tested. So these first few data, right, these first few data points maybe not so valid, right? So this is just like how you're doing your experiment, right? When you do measurements, your measurements must be well made, right? Without parallax error, without zero error and all this. Okay, so I would say these first few measurements, right, not so dependable. Okay, these later few measurements, you know, after the situation has stabilized, the hospitals are more aware, people are more aware, then yeah, maybe more doable. So let me do some adjustments, right, to remove these first few cases. So maybe around 15 onwards, right? Like that. Okay. So now based on this data set, the first 12 data points I ignore. Then Excel is really very cool. It can help us to draw a best fit line as well. Okay. So from the best fit line, not only can it draw the best fit line for us, it can also display equation on the chart. So without doing any calculation, what you call this? The program has done everything for us. Okay, we have our gradient here, 0.1114. Right, and so remember what this 0.1114 means. This 0.1114, sorry, the gradient equals to log 1 plus k, right? Remember from the equation just now? Right, and then this equals to 0.1114. Okay, and so we can use this to calculate 1 plus k, right? 1 plus k should be 10 to the power of 0.1114, right? Do you have a calculator handy? Can help me calculate this? 0.1114. So 1 plus k equals to, should be 1.2 something? 1.29? Okay, and so this gives us a k value of 0.29. So basically this is the average spread in UK. That means on average every 100 people that are sick, right, will spread to 29 new cases every day, right? And so this day by day this will compound. Okay, so comparing this with our other countries, right, you can see that Italy is 0.22 lower, okay, and USA is 0.31, slightly higher. Okay, so US and UK kind of on the higher end now, so a little bit worrying. Even though they started later, we can expect that the US will overtake Italy if nothing, like if people don't change their behavior very quickly, okay. So think about it. You remember in the past 2 weeks, the news and the ministers and all this, they always come out and say we have to observe good personal hygiene, don't go out you're sick, social distancing, all this stuff. So all these things, right, basically is trying to lower the probability of the virus being passed, right? And so basically what we are doing is we are trying to decrease the k value. Okay. Yeah. So basically trying to decrease the k value. Okay. And the effect of decreasing the k value. Now remember where the k value is. The k value is in the original equation. Is in the this term here, right? Which is then applied to the power t. Okay. And so the effect of having a lower k value versus a higher k value is that for the initial part of this graph, right, this exponential growth phase of the curve, right, lower k value means that you grow less steeply, right, as opposed to growing more steeply, right? Essentially, lowering the k value is what we mean by flattening the epidemic curve. Okay. Okay, so hopefully this was a good revision of our data analysis skills, how to linearize equations and do some calculations based on the graph and so on. Okay.